All right, thanks everyone. Thanks very much to the organisers for this chance to talk to you all. Can everyone hear me okay? So I'm going to be talking about some joint ongoing work with Johannes Kleiner. And we're going back now to the topic of IIT that we heard about a lot this morning. And the aim of what we're doing is really to take apart IIT a bit and look into how we can formalize the theory and take it to some new settings, so perhaps to address some of the concerns that came up in some of the talks earlier this morning. So we've already heard about it quite a bit. So IoT is all I'll say here is it's a leading theory of consciousness. Well, we're going to take it as a given here, essentially, and it states that, as we heard, that basically any physical system in some state could potentially have some kind of conscious experience, and it moreover gives an algorithm for telling you, firstly, a number as to how strong that experience would be, and also even claims to tell you something about the quality of that experience. And the way it does that is by examining the system and essentially looking how integrated its internal behavior is. So we had a nice introduction by William to the theory this morning, and we also had some problems mentioned with the theory mentioned by Adam. So this theory is undergoing development all the time. So I'm mainly thinking about IoT 3.0 throughout this talk. Some things that you might want to change about it, the fact that often the way it's defined is through lots of examples and so forth. So you might want a really succinct definition of the theory just to make it something that mathematicians and other people from technical background can really easily just dive into and start playing with. And something else, perhaps more important and perhaps more fundamental, is if you think of IoT as making a fundamental statement about consciousness, which it does claim to do, then you might want to be able to apply it to really any kind of physical system. Whereas at the moment, it seems to be only formulated in a way that would apply to quite simple, finite, classical kinds of ones. So to address both of these, what this talk is about doing is trying to formalize IoT in a new way that's hopefully clear, or at least like sort of simpler and potentially more abstract. But it makes it immediate to just generalize it to new settings. So particularly what we'll do is we'll define something called a generalized IoT and see how to get it. If you start from any kind of theory of physics that's described by what's called a process theory, you can essentially get one of these IoTs or some of these IoTs out of it. So for example, if you just plug in classical physics, you can get IoT 3.0 as it's normally defined. If you put in something like quantum theory, you can get a quantum version of the theory and so on. And if you don't care at all about IoT, hopefully there's still some interest here in the general methodology of trying to formalize and compare different theories of consciousness, and maybe some of the work about process theories as well. So what I'll do is I'll just dive into now trying to talk about what a generalized IoT is. And the game we're playing here is really looking at those IoT papers and looking at what went into being able to use the algorithm that they use to derive things like phi and the conceptual structure that we heard about, and not getting too tied down to the classical bits that were going on. So we're thinking about an IoT in general, so any kind of generalized integrated information theory. A neat way to think of it is just as some kind of mapping like we saw. So we're going to have a class of different types of physical system and states they can be in, and it'll send each of those states to some state of conscious experience, and more generally send each system to its space of all the different kinds of experience that it could have. So there's going to be these two classes and a mapping, essentially. If we start by talking about the systems, so if you look into what goes on in the algorithm and try and make a really minimal definition of what you need to be able to call something a system to apply it, this is what we ended up with. So we'll have this class here called sys of physical systems now that we're going to be looking at, and each one of the elements in here needs to have some basic features that let us talk about integration. So it needs to come with some sets. There'll be one that is just its states, because we need to talk about the experience of each state. And beyond that, it's basically about looking at some sets which talk about how we can decompose the system. So there's going to be some way of pointing to some other systems in your class that are called subsystems. And there's going to be also a set of these decompositions. And finally, when you've got a decomposition, you'll be able to make a new system using cutting, which we heard about earlier in the context of IoT. So roughly, we can see this. So here's the picture to have in your head is that you've got a system S. This is Z is a decomposition. So it's just a way of looking at your system. And here we're looking at it as consisting of two subsystems, M and M prime. And in order to be able to see how integrated it is, we need to be able to at least talk about what would happen if we had the same system, but we'd cut it so that these pieces weren't interacting anymore. So this is the picture. So now we've made this new system SZ, which is the cut one. But formally, all we really have here is a class of objects with these sets and little else structure. So this one's relatively straightforward. Now if we talk about the right-hand side of that mapping, we're going to be looking at a class that's supposed to model experience. So the elements of each of these, all the elements of this class are going to be some mathematical objects, each modeling the space of experiences rather than a single one. So each one of these things, which here I'll just call experience spaces for short, has to come with some features. And if these features not really coming out of a priori thinking about what experience has, these are just coming out of what we need to apply the IoT algorithm, or rather what you get when you look at the output of that algorithm. So what you get on each experience, well, the first feature you have is that it has an intensity. So for example, the phi that you get out at the end, this is a number. So we're modeling this just by saying that every one of these spaces comes with a sort of norm-like feature. And often what you also do in the algorithm is constantly talk about how close two of these things are together. So you need something like a distance. This doesn't have to be a metric in our setting, but you essentially want this to be a metric. And the final thing we'll have to do sometimes is take an experience and then just talk about having the same one, but with less or more intensity. And the easiest way to encode this in your set is just by having some kind of scalar multiplication operation around. This is a sort of mathematical convenience, really. So each of the elements of this space, of this class rather, are going to be sets with these features. And these are meant to just be some basic facts about different experiences that we can apply to them. To give a theory then, so I'm now going to give an addition of a generalized IoT, it's these two classes, and then you need to give some further stuff. The first thing you need to do for each system is give one of these spaces of experiences, but rather than the full experiences you can get, you just start from some simpler thing, which we call its proto-experiences. So this terminology I don't think appears in IoT, but we'll see what it corresponds to there in a minute. And then the final thing you need to give are these things that we did hear about called the cause and effect repertoires. And for us here, in the most general case, they're just some maps. But really, when you're working, these are supposed to come with some intuition about being about cause and effects in the case of IoT. So if you think about what this says, it says this first map, say the cause repertoire, when you've got your system and you've picked your state, for every pair of a subsystem and another one, it gives you a proto-experience. So this is like the value of your repertoire when you plug in some subsystem M and some 1P. So normally you've got like one called M here, which you call the mechanism, and one here, which you call the purview, and this gives you the value of the repertoire there, and that's the proto-experience. And the final thing you need is something here, which I haven't bothered making formal on the slide. It's just some facts about how these things decompose, because you need to assess how integrated they are. So if we look at IoT 3.0 in this framework, for example, okay, you have a class of systems, and they're basically finite sets that you can think of as being different states that a load of nodes can be in. So they have a decomposition into some nodes, and they also come with a sort of time evolution on them. So the states, more general states, would then be probability distributions over these nodes, and the proto-experiences would be the same thing. So they're also distributions. So essentially in IoT, everything starts from distributions, and then everything's built from these. In particular, repertoire values are also distributions, as we saw in the talk in the morning, and they essentially tell you something about the cause-effect features of your system. So the cause repertoire tells you how the current state at M is constraining what the previous states of P could have been. So that's, once you've given that data, you've now defined, in our sense, a generalized IoT. But the point of doing so is that it gives you this mapping. So really, another way to think about a generalized IoT is as a particular type of this map. So it's the map, like I mentioned to, now slightly more formally, between these classes. So you have your class of systems, your class of spaces of experience, and have a mapping between them. And moreover, this goes down to the level of state. So once you've got a system, you get this space of all of its full experiences now, not just as proto-experiences. And for each state, you get a value in there, which would be the experience in that state. So I haven't defined what this E of S is, right? And I'm just saying that's something you build out of this proto-experiences, which you specified using this algorithm, which we're just going to refer to as the IoT algorithm here. And I'll get to that probably later in the talk. And there's a final aspect that's specific to IoT, which is that you also pick out one subsystem of your system and say, this is the actual bit that's conscious. And that bit's often called the major complex. But if we look at just everything up to this point, I think this is a good way of thinking really about any sort of theory of consciousness that's about taking a load of material systems and saying what kind of conscious experience they are having. So this could be applied to all sorts of other theories, this sort of general schema. And IoT is just a specific way of getting such a map B. Having defined these things, and I'll talk about how you can get something slightly more specific, which is one of these IoTs out of a process theory, to try and give some of these terms a bit more meaning. So what is a process theory? I'll just be very vague about it here. It's a collection of things which here I'm going to call objects, and a collection of things that you think of as processes between them, and you draw these things with diagrams. And what's nice about them is that you can take your processes and plug them together to, hope that's okay. Get that thing over. To form new ones. So here we've got a process F from A to B, and this other one acting on a couple of different systems, and we've plugged them together to build a bigger process. And you can get lots of different types of processes here. So this one with no inputs you would call a state. This one you'd think of as a scalar. You'd call a scalar, rather. And you can make, the diagrams are very nice to work with, but you can make it precise by saying you're working in what's called a symmetric monoidal category. I think these kind of diagrams go at least back to Roger Penrose's work, using them to draw diagrams of tensor calculations. For us, we'll work with a process theory that has a little bit more of a physical intuition to it, and I'll just call those operational here. So that means that these kind of scalars correspond essentially to probabilities, but they're unnormalized ones, so we allow really positive real numbers. We also need something that's going to give us this distance d that was coming up earlier, and so we'll just assume we have this kind of structure where we can talk about how far states are apart from each other in our theory. And we have these features that let us discard certain objects. So the main things to think about then are these examples. So if we put in, we can talk about classical physics as being such a type of process theory now, where the sets, in a simple, the objects in the simplest case would be finite sets, and processes would be probabilistic kind of maps. Or you can do something new like quantum theory by looking at Hilbert spaces and now looking at completely positive maps. But there's really, I mean, these are very general, so you can talk about much more general process theories than these. If you start from one of these now, I'll just briefly talk about how you can get an IIT out of it. So what would we do? So we want to build one of these generalized IITs from our process theory. The simplest thing you can do is make a system just be an object of your process theory. You need some kind of time evolution, again, like we heard about in classical IIT. And the simplest thing you can do is then say that you just have a set of nodes. So these are just other objects in your theory, and you've written it as a tensor of these. So formally, any process theory comes with this tensor operation, which is just what happens when you put two objects side by side in your diagrams. So it's basically just a way that you've got an object, and you've got a way that you're thinking of it as made of certain parts. Those would be your systems. Just like we saw in IIT, then we could take our proto experiences and our states to just be states in the sense of our process theory. So these are processes with no input that run into our object. And I'll just mention that the diagrammatic languages process theories is very nice for talking about the repertoires as well, but I don't think I'll have time to go into that here. When you look at what you needed to make these repertoires, you end up finding that the simplest thing to have is just have a process for each one going between each pair of subsystems. So this would be the effect repertoire from M to P, and to get the actual value, you plug in a state here. And the diagram's quite useful for talking about these. So the simplest kind of effect repertoire you could write down is you just take your time evolution. This goes across your system, and you're just throwing away the bits that you're not looking at. So to get one, you have some freedom here in how you define these repertoires, but the process theory language is very nice for doing this. The point being now that normal IIT comes out as a special case of this approach. So if you start from this classical probabilistic theory, and you go through that procedure, then you'll get normal IIT 3.0. So as we saw then, the systems come with these finite sets with this decomposition. So here you're really thinking this set S in terms of IIT would be the state, would all be the sort of deterministic states of your system. And the general states, or the proto-experiences, would be distributions. But you can do something different now. So Zanardi and collaborators have defined another theory that they call quantum IIT separately. And you can actually get this out of the framework as well if you plug in quantum processes now. So here now your objects would be these Hilbert spaces instead, so they become the systems of your IIT. And you've got each one as a way of writing it as a tensor of some subspaces. Instead of being probabilistic now, your time evolution is completely positive, which is the corresponding thing in quantum theory. And now instead of distributions, you have the quantum version of states, which is density matrices, which can be unnormalized. And they would form your proto-experiences. But this is very general, so we can start making new theories in using this framework if we like. So say we think that both quantum and classical behaviors in the brain are, for some reason, both relevant to consciousness. And we might want a theory that combines both of these. So here's one where you just include both quantum and classical types of objects in your theory. You could work in something like the theory of finite dimensional C-star algebras. This is just models of things that include both classical systems and quantum systems together, and you could define your IoT in there. Finally, I'll come back now to talk a bit about the algorithm, which I didn't want to go into too much details with earlier. So we're back in the context now of generalized IoT, so we haven't necessarily got a process theory around. And we've got our repertoires and our proto-experiences. And I just want to talk about how this mapping is ultimately defined. So what we've done is look into the algorithm that goes on in IoT and just try to make it a bit more succinct. So something that you have to do repeatedly in the algorithm is look at how integrated things are. So I'll just say, let's suppose that we've got one of these experience spaces, and we've got some element in it, and we've also got like a sort of corresponding element for each decomposition of some structure. Once we've got that, we could view that, so we're basically seeing that as a way of decomposing our element. And we want to talk about how integrated it is as a whole. A way you can do that is just see how far away it is from all of these decomposition versions of the same element. And we can call that phi of e. And often what we want to do is rescale our element so that its norm, as it were, or its intensity was this phi value. And the final thing that you do a lot in the algorithm is you have a load of these elements and you just want to talk about which one has the most phi. And so you call that the core, the index which gives you the highest phi, you call the core. So these are just some mathematical definitions. The really point of doing them is just that once you've got them, you can talk about the IoT algorithm relatively compactly in that it can basically fit on one slide, which is nice because it normally takes quite a while. So if you've got a system in some state, the first thing you do is need to give every mechanism a concept, is the terminology. So you just pick every subsystem, you give it what's called a concept, which is an element of this space. So this is now again an experience space. It's a product of two ones. So a concept is just a pair of proto-experiences, and you get it by looking at the integration of these repertoires. After that, now I'll finally tell you what the space of experiences is. In IoT, in any IoT, we just say that an experience is a big tuple of all of these concepts, one for each subsystem. And the one you get is this what's called the Q shape. So you just got your concept for each mechanism, and you put them together. And then the point in the IoT algorithm is that its intensity should be related to its level of integration. So you rescale this thing, and that's your final experience in that state S. So you rescale this according to how integrated it is. So this intensity of the thing you get at the end is what's normally called the capital phi. And finally, then, the major complex you can also talk about in this language, and it's just the core of this Q shape when you're looking at all the ways you can vary it according to different subsystems. So I think it's a nice way to look at the algorithm. The main point being that it's relatively, it's just a way of writing the things that happen at the different steps in a common language, and that's useful. So this is definitely work, ongoing work. So if I just talk about what the point of doing this and where we can go in the future with it, I kind of think at the moment we've been talking a lot about states, so states of systems and states of experience. And I think generally a sort of process theory perspective is going to be a useful one in the future. So we'd rather like to talk about processes that are happening on the systems and how they affect our experience as a process as well. And if you're doing that, what you want to do is make these things sys and exp, not just be classes as they have been, but be categories now. In which case, the mapping that we talked about would be a functor between these categories. And this, I think, is going to be a nice way ultimately to formulate theories like this, and ultimately, hopefully any kind of theory that starts from just a load of systems and gives you some claim about consciousness. So here I've imagined global workspace theory has been formulated as a functor in a similar way. I don't know really anything about that theory, so if that doesn't make sense, just insert your own preferred sort of emergent theory there. Going back to IT itself, I also think category theory could be quite useful for thinking about this. So I didn't really talk about the technical issues with the theory, but one is that there's lots of points where you just assume that there's a unique subsystem with some property, but it's not really guaranteed to exist. So category theory has talked about the existence of unique things with some property quite well a lot, using features called limits and co-limits. So I think ideally the algorithm will be eventually formulated in terms of these things rather than even necessarily relying on the metrics. And I also just think the language of process theories is really perfectly suited to talk about a lot of the things that go into the intuitions behind IoT, including causality and integration of things. So this is because in a model category or process theory, sort of the basic element is this tensor symbol. So this is a way of getting two things and placing them sort of side by side, so not interacting essentially. And integration is all about contrasting your thing that you have with things that are just decomposable in non-interacting parts in this way. And a lot of work is already going on about looking at causality in these settings as well. So yeah, lots of stuff to do on this in the future, and I'd be interested in hearing what you all think about it. Thanks so much.